Good morning. In this video, we start Chapter 4. Chapter 4 is all about apportionment, and so as usual, what I wanted to start by doing is looking at what is an apportionment problem, what type of math do we need for this, and then discuss the different methods that we have in actually solving such a type of problem. So let's just dive right into it, and let's look at an example from the slides. So I'm just going to go ahead and read it out loud, and then we'll kind of talk about how do we solve this and how can we apply the ideas of apportionment to the real world. But parking on a certain college campus can be very difficult, and there are not enough spaces to go around. So for all of you PLNU students, you're probably familiar with this conundrum of why is there never a parking space? But it says, fortunately, not everyone is on campus at all times, and many people with parking passes actually walk, bike, or take the bus instead. There are 5 types of parking passes, and a number of passes of each type are indicated in parentheses. So there's faculty passes, to which there are 77 faculty members who have those passes. There are staff spaces on campus, to which we have 174 staff members. Upperclassmen spaces, 295, underclassmen spaces, 240, and also visitor parking spaces, to which we have 150 permits available. And if you're thinking about this problem as being a little unrealistic, typically when we're on campus, right, there's not this many different types of spaces, but you can kind of imagine like on Point Loma, you have like your orange spaces or your purple spaces or your green spaces or whatever, and those indicate different sorts of, allowances for who can park here. So one of the main problems that we're going to be tasked to solve, of course, is the campus only has 100 parking spaces, and if we're adding up the number of parking passes that are out there, we have way more passes than we have available spaces. But the question that we're going to be looking at is, well, if we have 100 parking spaces, how do we divvy those up between the different types of permits? Like which of those spaces should be painted orange and which should be painted purple or whatever? How many spaces should go to each demographic or each type of pass? It says to fairly distribute the parking spots, administrators wish to assign a number of parking spots to each type of permit based on how many people hold that permit. And this is the key idea behind apportionment, is we have a certain number of objects to distribute to a bunch of different groups. How many objects does each group get if it was to be done? Again, the question is fairly. And as we've seen in the past couple chapters, fairness is not a black and white issue, and there's some issues that can arise when we actually look into what actually happens. Let's just look at one example, and because I promised to talk about this back when we were in Chapter 1, about the U.S. Electoral College system. And at the time, we kind of when we were discussing weighted voting systems, how the U.S. sort of functions as a weighted voting system with 51 different voters, each state kind of representing, okay, how many votes is going to go to the leading candidate in that state. Then, the entire United States processes its vote to determine the president of the United States. But one of the things they brought up at the time is, well, how do we know how many votes each state should get? Like, why does California have 55, but Montana only has 3? And at the, one of the obvious reasons is, well, because each state has a different set of populations. And if each state is voting on the president, all states are not equal in terms of how many people it represents. So what you'd expect or what you'd assume is that these numbers are directly related to the size of those populations. But what actually a lot of people don't really know about the Electoral College is the balance of the number of electoral votes is not a properly apportioned set of numbers, meaning it's actually not exactly distributed. This is not fairly distributed based on the states. And so one of the things you might be wondering is, well, why isn't it evenly distributed or properly apportioned? It's due to the complex issue of weighted voting systems, in that if it were properly apportioned, there would be a lot of states that would be dummy voters, and a lot of states would have way too much power. So it wouldn't necessarily be fair in that regard either. But as we've kind of been looking at, fair is not something that's easy to attain, and sometimes we have to live with the weaknesses of our system. But this is a pretty big weakness that I wanted to share with you guys, because really the votes of the individuals in the United States are not equal. And I'm going to put that in air parentheses, or air quotes, not parentheses. What am I saying? But basically, let's look into this a little bit. So actually, again, in the slides, there's actually a link um, to a web page which gets into this issue. So let me go ahead and pop that up and look at this. But basically, you can find this link in the slides. It says how powerful is your vote. But basically, what this is a U.S. It's an apportionment map, which basically shows us the. Sorry, let me get this loaded before I keep talking. I'm having difficulty talking and doing this at the same time. Okay, let me get that in a point where you can see it. Cool. Um, so basically it's a power map which is saying in each state how many people contribute to those electoral votes. Like as we saw with Montana, it had 3 electoral votes. And if we go to this live map, you can hover over it and it will tell you. Actually, you can't quite see because I need to scroll back up. You can see what it says is Montana has 255,000 people per electoral vote. And if you do the math there and multiply by 3, what you can figure out is, well, what's the population of Montana by reverse engineering? And in this chapter, we're going to be looking a lot about how do we do this math and how do we apportion. And it's using a lot of dividing and multiplying, which we'll get to very soon. But anyways, and notice it has a vote power, 9th highest vote power. And if you go to some of the other states, typically the very small states have the highest vote power. Like looking at Wyoming, it's actually the highest vote power, which has 142,000 people per electoral vote. And if you go back to the electoral map, you'll notice that Wyoming also has 3 votes in the Electoral College. But those states actually have a pretty big difference in population. And so, cutting to the chase, and kind of what is the problem here, and what do all these numbers mean? Basically, if we're thinking about the weighted voting system for electing the U.S. president, each electoral vote is not equal, because in some states, like in Wyoming, 140,000 people make up 1 vote, but in Montana, 250,000 people make up 1 vote. So if you're thinking about the difference in these 2 states, they have the same electoral votes, but actually Montana has more people, meaning that each one of the votes, each individual person's vote in Montana has a little bit less of an influence in that weighted voting system. And if you look at certain states, like the biggest states tend to be at the hugest disadvantage in this sort of setup. If you go to California, for example, California has 508,000 people per electoral vote, which is 49th highest vote power, which basically notice that that's a lot more people per electoral vote. Even though California had far and away the most votes at 55, it's basically there's so many more people still are making up those votes. And if you go back and compare to Wyoming, it's like almost triple the number of people per electoral vote. So really, summarizing, our votes in California count for less in that weighted voting system, on a 1-to-1 basis for electoral votes, because there's so many more people that go into that vote. So basically in the U.S. system, votes are not equal. The votes of each individual citizen does not matter. And I mentioned this at the time. The U.S. Electoral College system is a weighted voting system by states. It's not really based on votes. And the president who has the most votes in the United States doesn't actually necessarily win. A president can actually win what's called the popular vote, but still lose the election just due to often a lot of these nuances. And typically the larger states tend to vote more towards Democrat, and the smaller states tend to vote more towards Republican. So there's a lot of argument about, is this fair? Should we change it? But as I kind of discussed before, change is very hard in a political landscape, because if one party is trying to initiate change, the other party is often strongly against it, because there's usually an underlying reason. It's not necessarily in the interest of fairness or math at all. It has more to do with power. But anyways, enough on that. Let's return back to the apportionment problem and continue with some terms. So let's define a lot of the basic terms of an apportionment problem, and then we'll try to wrap up this video and do some examples. Actually, it looks like my slideshow is still running, so my computer is not happy with what I'm trying to do. Okay, there we go. But basically, to start off with, what is apportionment? It's the act of sharing something fairly between several people or organizations. So like in the parking space example, we wanted to share a particular number of parking spaces between a bunch of different organizations, groups, or sometimes it's individuals, sometimes it's groups. And that example would be the different um, brackets, faculty, staff, students, visitors, etc. Um, so in these questions, and actually the terminology that the textbook uses is very programmed towards like a real like an election. Say for example, the United States, we have a say electoral college or a House of Representatives, where there's like a number of seats on the House, and the seats just correspond to well how many people can meet in this gathering. But I'll just go ahead and define the terms and just kind of know that sometimes the terms don't make sense towards a real problem, but we can still obviously try to understand what they're referencing. But the states are the persons or groups that have a stake in the apportionment problem. And so basically, in the Electoral College, each of the states is the states. It's like how many votes does each state get in that Electoral College, and it's kind of self-explanatory. And the number of states is just well, how many people do we have? How many objects, how many people are being distributed? I mean, basically, how many groups are there? And in the book, they use the capital N in this chapter to represent the total number of states. So in the United States, there would be N is equal to 51 due to DC. The seats are the objects that are actually getting apportioned, where the book uses capital M to stand for the number of seats. So in the Electoral College, I believe it's 530. I don't remember the number off the top of my head. I think it's 536. Or no, that doesn't make sense. Um, Whatever it is, you can look it up. But basically, there's a fixed number of seats, and those are going to be distributed to all the states, and all of those add up to the total, of course. Um, and the populations are basically the numbers which serve the basis of the apportionment problem. So in the Electoral College example that I was just describing, the populations would actually be the populations of each individual state. So how many people are in California would be the population of California. How many people are in Wyoming, and those are the basis for how those numbers are given out. And that was one of the issues with the Electoral College is it's not really apportioned. It's kind of apportioned and it's kind of not. And there's reasons why it's not apportioned directly via methods of apportionment that we're going to learn in this chapter. But let's return back to the parking space example, and let's try to figure out what are the states, what are the seats, and what are the populations. So going back to the same problem, basically there were 5 types of parking passes. These would be the states. The states are basically the different groups. So we had faculty, staff, upperclassmen, underclassmen, and visitors. So basically we had 5 states. It's how many different things are being distributed into. And the populations are going to be the individual numbers that are the basis of those things. So we had 5 different groups. Each of those should have their own corresponding number, and the numbers of each state dictate the actual apportionment process. So basically, this would be population 1, population 2, population 3, population 4, population 5. And then the total population would be the sum of all of this people on campus who need those parking spaces. So if you add up all 5 of those numbers, that would be our total population as well. And then lastly, the objects to be apportioned are the seats in these cases, which are the parking spaces themselves. Like in the Electoral College, it's like how many actual seats do we have and how many seats will each population get. And basically that will be, this will be N, this will be M, and this will be each of the P's. Adding all those up would be capital P, but P1, P2 would indicate individualized populations. And now to finish up with, there's a couple other terms which are very vital to an apportionment problem. First of all, we need to know what is our method of apportionment. And basically just to define what does apportionment method mean, it's a systematic procedure to fairly divide the seats to the states. So basically, well, what is the procedure? What are those processes? That's what we're going to be learning is, what are the different methods for actually doing the apportionment. And what are the outcomes? We're going to analyze again. Why are some of them unfair? What are some of the issues that arise with apportionment? But one of the key terms, well, this is the most important term in the entire chapter, is what we call the standard divisor. Each apportionment method is based on a standard divisor. The standard divisor is equal to the total population divided by the number of seats. Or in a mathematical formula, the standard divisor, SD, is equal to capital P divided by capital M, where this just represented the sum of all of the populations, and M represented the total number of objects to be apportioned. So if we were going back to the previous problem, if we wanted to know the standard divisor in that question, we would take the population of each of the total population of each of the states combined. So adding up all 5 states, we would get a total of 936. Dividing it by the number of objects, M, not by 5, but by how many things we're trying to give out, would be 100. It would leave us with a particular number to which we call the standard divisor. And basically, whenever you're doing apportionment, you need to start with this number. This is the key number, and we'll talk about why in a second, but I wanted to return to the previous slide. Why do we care about this calculation? What's the relevance of the standard divisor? But basically, it's a numerical value which is describing the ratio of what's the excess? How many more of this thing do I have than this other thing? And it's like really the basis of the key issue in the problem at hand, right? We had this many people, we had this many parking spaces. We have way too many people. How do we give them out? How do we actually distribute them? That's really the key of the issue. And if you just take that ratio, that's a very helpful number to understand. And this sentence doesn't actually make sense, so I need to fix that. But I'll probably forget again, as I always, this error has been there in my slides for a year and a half, and I keep forgetting to change it. But basically, it's describing, if we think about the units or the values that we're doing, basically we have a number of people and a number of objects which are getting this people, and which are going to be given to those different groups of people. And basically, like in the case of the parking space conundrum, the standard divisor came out to be 9.36. And so really what this is saying is I have this much too many people corresponding to the objects which I'm trying to give out. So I kind of think of this as for each parking space that's supposed to service or provide a parking space for 9.36 people. Obviously that's impossible because you can't fit 9.36 people in a parking space. Excuse me. But it gives us that it's kind of like an idea behind how much too many. I know this doesn't make sense, but if you can see what I'm saying, how much too many do I have? And basically it's kind of cutting out a particular issue. Each parking space will need to serve 9.36 people, which is not a possibility, but sometimes it's a reality that we have to live with. And in Point Loma, we all wonder, well, why can't we have parking? How, can't we just do something about this? A lot of times there's limitations on the space we can build. Like sometimes we can't build another parking lot, or we can't build another level to our parking garage. It's just not allowable by the city, or a lot of times there's various reasons. But it's not necessarily the administrators don't care about us, but they often have other needs that are taking priority, and we can often make do if we do a little bit of math to actually finding those values. And so we're almost done with this video. I know this one's getting longer than I had intended. But also then what do we do with the standard divisor? So basically in an apportionment problem, you're always going to be starting with the standard divisor and dividing by it into each of the populations. So what we call the standard quota in each of these problems, basically if we're trying to figure out how many parking spaces should each pass get, returning to the original problem, right? We wanted to know, well, how many of these 100 spaces are going to go to the faculty? How many of those 100 spaces are going to the staff? How many to the upperclassmen, underclassmen, and visitors? And obviously what you could do is you could say, well, why can't each just get 20, 20, 20, 20, right? And we just equally distribute them. We have 5 things. Why don't we just split them up, divide by 5, 20, 20, 20, 20. But obviously the issue with giving 20 to each of the states is that, well, we have way more students. If they only have 20 parking spaces, that's going to be really, really horrible. And even the faculty might not be happy with 20, but in reality, since there's way more students, they should be getting a bulk of the spaces. It should not be a direct division. And there should be some math that actually goes into this. It shouldn't just be assigned randomly or evenly. And that's the other thing. Even does not mean fair, because it's really dependent on the size of each of those groups. So how do you ensure that they actually get the proper amount? Well, that's what the standard quota is. The standard quota is the exact value each state should get under perfect division. So in those problems, if we wanted to know exactly how many should the faculty get, exactly how many should the staff get, basically what we'd be talking about is what's the standard quota for the faculty, what's the standard quota for the staff, et cetera, et cetera. And formulaically, it's very, very simple. If you take each individual population and divide by the standard divisor, that will give you the individual state's standard quota. So here we're just letting q, little q sub 1 be the standard quota for state 1, Q2 be the standard quota for state 2. And basically all this is saying is to find each state standard quota, take their population, and divide by the standard divisor. Or let's actually put some numbers to it in this problem. Let me go back to the actual slide. Let's say we wanted to find the standard quota for the faculty. Since we know the standard divisor, and this is, I'm going to say this probably a lot in the remaining videos, is the standard divisor is the key. That's the number you need to know. Once you know that, it becomes very easy to solve going forward. So that's the one main thing you should always keep in mind in an apportionment problem. But basically, we had 77 faculty members, so that was their individual population. If we divide by the standard divisor, this will give us the faculty standard quota. And if we do that, what we get is the faculty have a standard quota of 8.22 or 8.23, depending how we're rounding. And what does this number mean? Basically, this number means, well, what is the standard quota for the faculty? How many parking spaces should they get? And one of the obvious issues that arises when we're doing these calculations is we're doing division in order to find this, right? We're doing a bunch of dividing to figure out how should each of those parking spaces be divided into those numbers. And the issue that we get is with division, a lot of the times when we're dividing, especially by a decimal number, we're not going to get a nice whole pretty answer. We're going to get an answer like 8.2, where you can't give the faculty members 8.2 parking spaces, because what is 0.2 of a parking space, right? I mean, maybe you'd say, okay, maybe that's a motorcycle parking space, or, putting the silliness aside, it's not an option. So, well, what you would think is, well, okay, we'll just round that to 8 and give the faculty 8 parking spaces. And that's not necessarily wrong, but one of the issues that we're going to look at is rounding causes a lot of problems with proper apportionment. This is something the founding fathers discovered when they were trying to set up all of the elements of our political system, and a lot of the different methods that we're going to talk about were invented or discovered or really used by different U.S. presidents. And the reason why they kept changing the method was, well, a lot of times they were trying to work the system in a way, or trying to just be more fair, however you want to look at it. But anyways, this highlights the issues with apportionment. And let's just go ahead and finish the slide, and we'll get into an example in the next video. Basically, what we do with the standard quota is we could sometimes round. What we're going to need to do, right, is round it. And so in the case of getting the standard quota, we could either round it up, we could round it down, or we could round it conventionally. And sometimes, and we refer to each of those by upper quota, lower quota, and rounded quota. So if we take 8.2 and round it down, we would refer to that as the lower quota. Basically, 8.2 is the amount under perfect division that state should get. The lower boundary on that is 8, right? If we round it down, that's basically, well, the minimum. We could also round 8 up, which we would call the upper quota, which would be kind of like the upper limit of how many they should get, either 8 or 9 at the end of the day. And then we could also round it conventionally. In the case of 8.2, of course, that would be rounded down under conventional rounding, which we would just sometimes call the rounded quota. And actually, one of the last methods we're going to discuss is a method of rounding which is a little different than conventional rounding. But anyways, if you ever see these terms lower quota, upper quota, or rounded quota, that's just all it's referring to. Find the standard quota, round it properly. And that will wrap up our introduction video. So I know that was quite long, but apportionment is kind of a complex issue. There's a lot of numbers, and what I'd strongly recommend is being organized. And in the packet, what we're going to do is look at some examples of apportionment. And there's a lot of times in the packet there's tables presented, and it's very useful to use these tables to practice with apportionment. So again, as usual, I'd recommend using the packet, printing it out, and trying to practice doing the math on pencil and paper, because it's very hard to kind of understand the process of doing this without actually doing it yourself. Anyways, see you in the next video.